Hi, this is Nelson Yanowski. The class is Discrete Structures. We're doing section 13.1, which is about predicates and quantifiers. We're doing the homework problems. Here's the homework problems that we're doing. There's actually a lot of problems because there are a lot of different parts to it. So we'll be busy here for a while. And we might do some of them a little bit quicker. Okay? Okay, so let's do number 2. Okay? P of m comma n means m is less than n. Okay, that's what it means. Okay, they want us to do universe of discourse. Universe of discourse. They did this for the natural numbers in the book, which you should read. But now they want you to do the universe of discourse as z. Okay, let's go through it. Okay, let's do this. There exists. Oh, so this is A. There exists an n. There exists an m such that P of m is, well, you know what? Let's not use P. Let's use m less than n. M is less than n. Okay, what does this say? Give me any, there is some number, and there is another number such that m is less than n. Yes, that's true. There are two numbers where one is less than the other, one is greater than the other. Okay, so pick any number. 15, well, 14 is less than it. Pick any number. 93, well, 25 is less than it. So this is true. Okay, pick any number. 0, yeah, negative 1 is less than it. We're talking about this. That wouldn't be true in the natural numbers. Okay, great. Let's do B. What's B? For all n, for all m, okay, what does this say? This says, take any number whatsoever, any number is less than it. Now that's not true. 53, well, 75 is not less than 53. So that's not true, so this is false. Okay. C. For all n, there exists an m such that m is less than n. Let's go through that. Okay, take any number whatsoever. There's another number that's less than it. That's true. 52, well, 25 is less than 52. 7, well, 3 is less than it. 0, well, negative 1 is less than it. Negative 5 is less than it. So this is true. It would not be true in the natural numbers. Why? Because 0 is nothing less than 0. Okay, good. D. There exists an m such that for all n, m is less than n. Okay, is this true? Is there some m that's such that every other number, for every number, is greater than it? No, it's false. Okay, this is false. If I was to say negative infinity, then this would be right, but negative infinity is not an element of z. Okay, this in the natural numbers, this would be true. This m would be 0, and everything is, well, even 0 is not true. It's not true in the natural numbers either. Why? Because 0 is not less than 0, so it would be false there too. So this is the way you have it. Okay, good. Anything else? Okay, good. Next. Okay, now we do 3. Okay, 3. Okay. Determine the truth values for the following where the universe of discourse is n. So we're talking about the natural numbers. Okay, good. And let's do it. For all m, there exists an n. For all m, there exists an n such that 2n is equal to m. Okay. Any number is twice some number. Is that true? And the answer is no, this is false. It's true for even numbers. An even number is twice some number, but what about odd numbers? It's not true. Okay, so this is A, so it's false. This says every number is even. That's not true in the natural numbers. Okay, let's do this. There exists an n such that for all m, so B, there exists an n such that for all m, 2 to the, let's follow exactly what they're doing. There exists an n such that for all m, 2 to the m, 2 times m is equal to n. True or false? Okay, let's see what that says. Is there some number that's equal to 2 times every other number? That's false. Even take the number 10. It's 2 times 5, but it's not 2 times 3, and it's not 2 times 0, and it's not 2 times 5. So this is false. Okay, C. For all m, hold on, there exists an n, you have to be careful here, okay, such that 2 times m is equal to n. Let's see. 2 times m is equal to n. Is this true? Take any number, multiply it by 2. Does there exist an n that's equal to it? And the answer is yes. This is true. Take any number whatsoever. 54. Well, 108 will work here. 23. Well, 46 will work here. So this is true. Okay. D. There exists an n such that for all m, 2 to the n, 2 times n, is equal to m. Okay, is this true? Let's see what it says. Let's just make sure we wrote it right. This is D. For there exists an n such that for all m, 2 times n is equal to m. Is there some number such that for every m, is that, no, this is false. This is false. Okay, finally, E. I think we did E. What is E? E says for all m, for all n, it's false that 2n is equal to m. Okay? This is false. Okay? We did this in class. Okay? I'll give you one where they are equal. Take m to be 8 and n to be 4. Okay? Then they will be equal. 2 times 4 is equal to 8. So this is false. It's not always that they won't be equal. Sometimes they are equal. So if you say they'll always be not equal, that's false. Okay, very interesting. 4 falses and 1 true. And that's interesting. Okay, next, number 4. Number 4. Okay. Determine the truth values of the following where the universe of discourse is the real numbers. So now we're talking about the real numbers. Okay, now let's do A. Okay, for all x, there exists a y such that x times y is equal to 1. Always got to be careful with one number. Okay, let's see what this says. Take any number whatsoever. There is a number such that when you multiply it, you get 1. So take the number 3. There's 1/3. 3 times 1/3 is 1. Take the number 506. Take the number 1 over 506. 506 times 1 over 506 is equal to 1. So it works a lot. But there's one number where it doesn't work. Ready? Take the number 0. There's no number y such that when you multiply x times 0, 0 times y is equal to 1. None. So this is false. It has a unique counterexample. 0 is a counterexample. Is the counterexample. It's the only one where it doesn't work. Good. B. B. There exists a y such that for all x, x times y is equal to 1. Is that true? Is there some number that when you multiply it times any number, you get 1? And the answer is false. No, it's not true. We talked about multiplying and getting 0. That there is, but this there isn't. Next, C. There exists, gotta get the letters right, x, there exists y such that x times y is equal to 1. Is this true? Yes, in fact I did an example. 3 and 1/3, 3 times 1/3 is equal to 1. 5, so this, I'm sorry, this is true. There is such numbers. This is true. Okay, 506 times 1 over 506 is equal to 1. Negative 18 times negative 1 over 18 is equal to 1. So that, yeah, that's true. There are some. Okay, okay, D. Okay, actually we did D. For all x, for all y, x squared plus y squared is equal to x squared plus y squared. Okay, this is false. This is false. Okay, this is false. Why is it false? Because it's not true. We did this. You need a plus 2xy in there to be true. Okay, and E we did in class, so we're going to leave that alone. Great. Let's do number 5. Okay, the answer to E was 0 is the counterexample. Okay. Right. When y is equal to 0, it works. Okay. Write the following sentences. Now we're doing 5. 5. Write the following sentences in logical notation. Be sure to bind all variables. When using quantifiers, usually specify universes. Use R if no universe is indicated. Okay, so we're going to write the sentence. Ready? So let's write it in English. Yeah, well, no, you don't have to write it in English because you have the book in front of you. And you worked out the problems by yourself. Let me just write it like this. Okay? X is less than y. And y is less than z. Then x is less than z. Okay, like this, and like this, and like this, and like this. Hold on, we're not finished. We have to put quantifiers in this, and so this is for all x, for all y, for all z. This is true. If x is less than y and y is less than z, then x is less than z. That's true. Okay, B. For every x greater than 0, there exists an n in n such that x is greater than n. Okay, so what does it say? For all x, there exists a n such that n is greater than x and x is greater than 1 over n. Okay, I'm going to assume that this is all about the real numbers. Okay. By the way, they don't ask us to say if it's true or false, so we don't have to say if it's true or false. Just write it. This is true. I think this is true also. I just have to worry about x. 0. 0. But I think it's true about. Maybe it's not true about. Oh, anyways, they didn't ask us to say whether it's true or not. Okay. Next, number 5. C. For every m comma n, there exists a p. Oh, I'm sorry. This is n in n. Okay, good. Let's do this. For every m comma n, there exists a p such that for all m, for all n, okay, let's write it like this. M is in n, and m is in n. Okay, there exists a p, implies there exists a p such that m is less than p and p is less than n. Okay, that's C. D. Okay, that's D. So this is A, B, C. Let's do D. There exists a U. U is going to stand for unit, such that U times n is equal to n for all n. Okay. Anyways, the answer is yes. This is true. What is it? U equals 1. 1 times n is equal to n. Is that true for everything? What about 0? 1 times 0 is 0, so it's not true, it's false. Okay, great. Let's do, we're still up to 5, we're up to 5e. I think we did 5e in class. No? Yeah? Maybe. Okay, let's do it quickly. 5e, for all n, there exists an m such that m is less than n. Okay? Okay. Fine. 5f. So this is E. 5f is... Okay, 5f we did in class. Good. Number 9. Specify the free and bound variables in the following expression. Okay, so we did this in class. Let's do this. Number 9. Okay. A. What are the free variables? Free is y. Is y. And bound is x and z. Bound is x and z. Great. Number B. Again, they give you the formulas. You have it in your book. So the free, what's free is y and z. And the bound is x. And C free is y, and the bound is x and z. Okay. Okay, we got to get another one of these. Okay, so that takes care of 9. Now we're up to 12. Oh, that's no good. That's no good at all. That's no good at all. Let's see what 12 is. Can get nicer than that. Okay, number 12. Consider the proposition for all m for all m, number 12, for all m, there exists an n such that m plus n is equal to 7. Okay. Is the proposition true for n, for the natural numbers? So now we want to know, A, in the natural numbers, is this true? Take any number m. Is there some other number? Is there some number such that m plus n is equal to 7? And the answer is false. It's false. Okay. Take the number 53. 53. You can't add any natural number to 53 to get 7. Okay. Next. Okay. Is the proposition true for the universe of z? Okay. How about z? Okay. Take 53. Well, 53 plus negative 53 plus, no, minus something is going to equal to 7. So 53 minus 40, 46, let's see, it's a 4, it's a 13 minus 6 is 7. Okay, okay. So, yes, 53 plus negative 46 is equal to 7. Take any number whatsoever, you're going to always find n is equal to, so let's do this, m plus n is equal to 7. So you want to find n, so simply subtract m from both sides. So n is equal to 7 minus m. So you give me a number, m, and I will find an n for you. So this is true. Okay, that's very good. Next, number 14. Number 14. Consider the expressions for all x. Let's do this. For all x, there exists a y such that x squared plus 1 times y is equal to 1. Okay, so let's do this. Okay, first, they want to know about the natural numbers. Is this true in the natural numbers? Okay, and the answer is no. Why? Take x to be 53. 53 squared is some humongous number. Plus 1 is some humongous number plus 1, right? Okay, there's no way you're going to multiply that big number times y to equal to 1. So I'm going to say that this is false. Doesn't work for 53. It doesn't work for most numbers. Let's see, maybe it'll work for 0. I don't know. Maybe it'll work for 0. Let's see. 0 squared is plus 1. 1 times 1 is equal to 1. So yeah, it will work for 0, but it has to work for all x. Okay, so it's false. Next, B. Is it work true for q? Okay, so this is a little bit more complicated. Okay, so pick a big number. Okay, well, I think it is true for 2 for let's just try x is equal to 1. So then this becomes 2. 2 times a half is equal to 1. Right, so that works. 3. Okay, so let's do this. We have AB squared plus 1. Let's write this as b squared over b squared times y is equal to 1. So this becomes a squared over b squared plus b squared times y is equal to 1. Okay, I'm going to leave this alone and see. I'm going to leave this. This is about the real numbers. I suspect that they're going to give you something like this. I think it's true for both. Oh, yeah, why? Set y equal to b squared over a squared plus b squared. Give me any rational number, a over b, then set y is equal to that, then this just cancels with this cancels with this, you're left with 1. The same thing is true for this. So I think it's true for here, and it's true for here. Okay, I could be wrong here. I'm sure if I'm wrong, it'll be, everyone will point out my errors, and it will be in the comments. But I think it's true. Okay, next, number 15. Okay, 15 is about, there is a unique x, p of x. So this is another quantifier. We did this before. How does it go? There's a for all quantifier, there's an existential quantifier, which means there's one or more, and there's a unique quantifier. Okay, so we did one of them. Okay, how about this? Okay, so let's do A. And I think they want us to state it and tell if it's true. Okay, so here, the first one, A is, the universe of discourse is the real numbers. There's a unique x such that x plus y, I'm sorry, I didn't say it right. For all y, there exists a unique x such that x plus y is equal to y. X plus y is equal to y. For any y, there's a unique x, and the answer is yes. This is true. X is equal to 0. 0 plus y is equal to y, no matter what you do. Okay? B, and that's the only number that would do it, so this uniqueness works. Okay? The equation x squared plus x has a unique solution. For all x, no, there exists a unique x such that x squared is equal to x. Okay, assuming this is the real numbers, okay, assuming it's the natural numbers, this is true. 1 squared is equal to 1. Assuming it's the z, the answer it's false. Okay, so this is for natural numbers, it's true. It's false for z. Why? So it's true for this. Why is it false? Because 1 squared is equal to 1. No. Okay, it's true for z also. Oh, I'm sorry. It's false for both. Okay? 1 squared is equal to 1. Yes, that's true. 0 squared is equal to 0. That's also true. So it's false for both. It's not unique. False. 1 and 0. It's true. 1 squared is equal to 1, and 0 squared is equal to 1. So it's false. It's false in the natural numbers. It's false in the C. Okay, C. Exactly one set is a subset of all sets in P of n. Take P of n. This is the set of all integers. Okay, there's one subset that's equal to, and that's true. So there exists one set such that for all t, t is a subset of the natural numbers, implies S is a subset of T. Okay? And that one set is the empty set. The empty set is a subset of every other set. Okay? D and E we did in class. One we talked about an onto function, and one we talked about a one-to-one and onto correspondence. Okay, that takes care of that. Have a wonderful day. We'll do section 13.2 in a few minutes.